In the previous video, you saw the power spectrum from one electrode, but we have 55 channels here, so we can actually create 55 spectra. Now, we could make 55 different figures to show us the data from each channel, but as you can imagine, that's both tedious and not very useful. So in this video, we are going to compute the power spectrum over all of the channels, averaged over all the trials. We don't need the single trial data anymore. So we're going to compute the power spectrum average over all the trials, store those results in a matrix, and then visualize that matrix. So the x-axis of this image is the same as the x-axis in the previous video, which is frequencies. But now the y-axis actually shows electrode index instead of power, and the color is now showing the power. So each row in this matrix is the power spectrum from one data channel. This is a pretty neat way of visualizing the data because we get to see all of the channels, so the power spectrum from all of the channels at the same time. On the other hand, this y-axis here is arbitrary. These are just, the order in which the channels appear in the data matrix. So what we're going to do next is sort this data matrix row-wise such that the anterior channels, so the channels that are closer to the face, are here at the bottom of the matrix, and the posterior channels, so the channels towards the back of the head, are plotted up here towards the top of the matrix. Now keep in mind that these two images show exactly the same data, it's just that the rows are sorted differently. Now what you see when you look at these images is there's a lot of yellow over here, so relatively high power at low frequencies, which goes blue as we go to higher frequencies. This is the 1/f, so the decrease in power with increasing frequency. And you also see these vertical stripes. Here this corresponds to peaks in the power spectrum at 20 Hertz and 24 Hertz. These are the two stimulus flickering frequencies that were closest to the center of the screen. So not surprisingly, in this sorted image, you see a stronger response towards posterior channels, which is not surprising given that this is reflecting a cortical response to a visual stimulus. So we should see maximal energy at the back of the head. Okay, so now we're going to switch to MATLAB and create these two graphs. The first thing that we are going to do is compute the power spectrum, so the FFT, over all the channels, and then average over all the trials. So this is pretty similar to what we did in the previous video. So in fact, I'm going to start by pasting in a line of code. This is just a line from the previous video where we computed the power spectrum from one channel over all the trials. Now here, we want to compute the power spectrum over all of the channels. Of course, you can do this in a for loop, but you now know that the FFT function can accept matrix input, and we just have to be mindful to specify the correct dimension to compute the FFT over. So now we want not just one channel, but all of the channels. So in fact, I'm going to delete all of that indexing here. So we input this three-dimensional matrix, and by looking at the sizes of the matrix, we can confirm that we want to compute the FFT still over the second dimension, which is the number of time points. Okay, so then let's see, I think I will even just delete some of this and put that up here. Okay, so this gives us the power spectrum over all of the channels, all of the frequencies, and all of the trials. And now we want to average over all of the trials. So I am going to use the mean function. And of course, we need to think about which dimension that we need to compute the average over. So just to make sure that we can think about this in the right way, I'm going to copy this, which is the input, into the mean function, and write size of this input, and we want to average over trials, which is the third dimension. So therefore, I will write comma 3. So that's going to make sure that we are just averaging over trials. Okay, now I'm going to add a little normalization factor. I'm going to divide by the number of time points. I'm going to discuss this in a few moments. So let's just run this line of code, make sure we don't get any errors, and check out the size of this. So this is channels by frequencies, and we don't have a third dimension of trials, which we expect because we averaged over those trials. Now, this is a pretty long and dense line of code. And if you find a line of code like this to be intimidating, particularly when you are just getting going with MATLAB, then you should feel free to break up this line of code into several other lines of code. For example, you could put the FFT on its own line of code. So yeah, let me just show you what that looks like. So you could say, temp FFT equals this, and then the input here is going to be temp FFT and so on. And if you want, you could even put this computing the magnitude and then squaring that, I guess it should be like this, into its own line of code and so on. So this is not correct code. I just want to illustrate the concept of breaking up a dense line of code into multiple lines of code. If that helps you better interpret the code and avoid making mistakes, then definitely feel free to do that. Okay, so now we have our data matrix and we want to show it in an image. So image scale, this is a function that we used in the previous module. And so this part isn't so difficult. We want to plot all channel power. And then remember, we don't want to plot all of the frequencies. We only want the positive frequencies. So the first 1025. So we want to visualize all of the channels, and 1 through length hertz is very similar to plotting the image. Okay, so let's see. All right, so all we see is a very nice shade of purplish bluish, but it doesn't really show us anything terribly interesting. Now, this is actually analogous to the previous video when we first made the plot of the entire power spectrum all the way up to 256 hertz or whatever this goes up to, where the 1 over f was so dominant at the very first few frequencies that it obscured the rest of the plot. So let's run this next line of code where we are setting the current axis, the current x limit axis. All right, so hopefully this will look a lot clearer. Oh, and it still looks like a bunch of bunny rabbits bouncing around in the snowstorm. What is going on here? Well, if we look at the x-axis here, it's going -3 to 0. These are not sensible values. So I don't know who writes this code, but there's clearly someone who has a bizarre sense of humor. I think in the previous video we did 5 to 30, or maybe it was 3 to 30. But anyway, this should be pretty good. All right, this looks really nice. Now we see exactly the matrix, the image that I showed in the slides. So again, each row in this image, each row in this data matrix is a channel, and the columns correspond to the frequencies. And we see peaks here at 20 hertz and at 24 hertz. Okay, so this all looks good, and then we're going to add a color bar. Now, I would like to very briefly draw your attention to the numerical values here. These color values, these are going up to 0.2 at the highest level here, whereas the power spectrum from one channel went up to, 10 to the 6. So over 10 to the 6. So these differ by 7 orders of magnitude, this plot versus the color plot here. Now, the reason why those two differ, it has nothing to do with an image versus a line plot, and it's not about computing the power for one electrode versus all electrodes. It's all about this little normalization factor that I added over here. Now, on the one hand, there is a deeper theory to what these normalization factors are for, and that would be something you would learn about in a course on the Fourier transform. So that theory is outside the scope of this course, but I do want to draw your attention to these normalization factors. Signal processing and statistics and data analysis and image processing is full of normalization factors. And those normalization factors are sometimes arbitrary and sometimes very important. So it's good to be aware of where there are normalization factors and when they are and aren't useful for interpreting your results. Okay, anyway, now we want to make the second graph, and that is basically the same data. So we've already computed all the data we need. We just need to sort by the x-axis coordinate, the x coordinate of the channel location. So just as a quick reminder, we want EEG.ChanLocs, and let's look at electrode 22. So we can see its x-axis coordinate is -76. And let's try electrode 52, its x-axis coordinate is minus 44. So these are the numbers that we want to sort by. So we can write sort, function is sort, and then I'm using square brackets here to concatenate all of the x-axis values from all 55 channels. So that looks like this. This gives us a vector. All right, so now we are going to sort these results. So you can see in the output here that we get sorted values. They start from being large magnitude negative to large magnitude positive. Now we don't actually care about the actual sorted values. What we care about is the indices that tell us which channels go in which order. So that is actually given to us by the second output. So I'm going to use a tilde here to suppress the first output, and I will write sort x idx equals. So here we have the first output, which we are going to ignore, and we're going to get the second output, which is the sorting index. So now let's have a look at that variable. So this vector is a bunch of indices, and this tells us that the electrode with the most negative x-axis coordinate is electrode number 25. So these are the electrodes that are furthest in towards the back of the head, and these are the electrodes that are closest to the front of the head. Okay, so therefore, what we are going to do is make this image again, but now we are sorting by this indexing variable here. Now notice here, I'm not actually changing the order of this matrix. That's important to keep in mind. It could be in some cases that you want to change the order of the actual data, but in this case, I don't want to do that. And that's because in the next couple of videos, we're going to be making topographical maps using these data. And the topographical maps need to be made assuming that the data are in their original order. Okay, so that means I'm only sorting the rows of this matrix inside this image and not in the data matrix itself. I'm not changing the original data matrix. All right, so let's run this. And very good, this looks like what we saw in the slides in the beginning of the video. So again, we have all the rows in this matrix now sorted such that the channels at the back of the head are at the top of the matrix and the channels at the front of the head are at the bottom of this matrix.